Alright, let's look at example 3. Evaluate the following integrals using the given substitution, leaving your answers in exact form. So let's look at 3a first. This is the integral that we have to integrate. And this is the given substitution. T equals to tangent theta. So we have learned integration by substitution in the previous chapter, involving indefinite integral. And now we are looking at evaluating definite integral by substitution. So from the previous lecture, we know that we need to make this d theta in terms of t, sine square theta as well in terms of t. And for definite integral, we need to make sure that the lower and upper limit change correspondingly as well. So just remember, for definite integral involving substitution, we have 3 things to take note. This has to be changed in terms of t, this as well, and the limits. Alright, let me bring your attention to the working on your right hand side. So we're going to break this working here into 3 different parts. The one in green will be the working for this. The one in blue will be the working for the lower and upper limit. And the one in yellow will be the one for the sine square theta. So we are given the substitution t equals to tangent theta. So if we differentiate with respect to t, what we end up having is 1 equals to secant square theta d theta dt by implicit differentiation. So rearranging, we will have d theta dt equivalent to 1 over 1 plus tangent square theta, because secant square theta is exactly 1 plus tangent square theta. So alternatively, you can actually differentiate directly in terms of theta. So you get dt d theta is secant square theta. So in other words, d theta dt will be equivalent to 1 over secant square theta. So it turns out to be the same answer here. So since tangent theta is t, so d theta dt will be equivalent to 1 over 1 plus tangent square. So now we are ready to actually change our d theta in terms of t. So d theta we can actually see as d theta dt dt. So that's the reason why you have this step here, whereby d theta dt is over here, dt is right here. So let's look at the yellow part. We are given t equals to tangent theta. So in other words, tangent theta is t divided by 1. So looking at the right angle triangle, if this is our theta, since tangent is opposite over adjacent, so t divided by 1 means that this is t, the opposite side, and the adjacent side is 1. And by Pythagoras theorem, this gives us square root t square plus 1 for the hypotenuse. Why are we finding the hypotenuse? because we are actually finding sine theta in terms of t. So since sine theta is opposite over hypotenuse, we will now have sine theta as t divided by square root of t squared plus 1. So the last thing that we need to do is changing of the limit. This is very important because many a times students forget to change the lower and upper limit. So now, earlier we have theta equals to 0 and theta equals to pi over 4. So we need to change the limit accordingly. When theta is pi over 4, t being tangent theta will give us 1 because tangent pi over 4 is 1. And when theta is 0, tangent 0 is 0. Therefore t equals to 0. So change correspondingly when theta is 0, t is 0. When theta is pi over 4, t is 1. That's how we change the lower limit and the upper limit. Next, simplifying this expression here. We're going to arrive at this fraction. And further simplify, I should get 1 divided by 3t squared plus 1. And based on what you have learned in the topic of basic integration technique, you should be able to arrive at this particular step here. So placing in the 1, you'll get tangent inverse root 3, and placing the 0 in, you'll get tangent inverse 0. So evaluating the answer, you will end up having this as your final answer. Alright, let's look at example 3b. We are given this integral. We are to evaluate it using the given substitution u equivalent to root of x cubed plus 2. So from the previous example, we know that we have 3 things to do when evaluating definite integral involving substitution. So number 1, we need to change this dx in terms of u for this case. So number 2, x has to be changed to in terms of u as well. And last but not least, the most important one is the lower and the upper limit. Because most of the time students tend to forget about this lower and upper limit. So we deal with this dx first. In our mind, we know that dx is actually dx du. So what we need to do now is to find out what is this dx du. So based on the substitution given, we know that we are given u equals to root of x cubed plus 2. So to find dx du, we have to make x in terms of u first. So what we have now is root of x cubed equivalent to u minus 2 and x cubed equivalent to u minus 2 square, and x will give us u minus 2 to the power of 2/3. So dx du gives us 2/3 u minus 2 raised to the power of negative 1/3, which is equivalent to 2 over 3 u minus 2 to the power 1/3. So since dx du is this, we can simply replace the dx du as this. So now what we have is dx du, and this is du. Now, this root x here, when you do a replacement, you will have u minus 2 to the power 1/3. This x cubed here will give us u minus 2 whole thing squared. And the limit, how do I change the limit? Correspondingly. So when x is 0, what is our u? So when x is 0, if we do a simple calculation, u is equivalent to root 0 cubed plus 2, which is 2. And when x is 1, we'll have u equals to 1 cubed plus 2, which gives us 3. And that's the reason why when x is 0, u is 2, when x is 1, u is 3. So now after simplifying this whole expression right here, we're going to end up having this. But usually after the process of substitution, it shouldn't be that tough evaluating this integral here. So is this something very familiar to you? Is it something that you have come across in the previous lecture on integration technique? So in fact, one of the formula that we have learned is integrating 1 over a squared minus x squared dx gives us 1 over 2a ln of modulus a plus x over a minus x plus c. So in this case, this 2 here, we can see it as root 2 whole thing squared. So in other words, yes is in this form. We can actually proceed on to use this formula to evaluate this integral. So what we have now is 2/3 1 over 2, the a being root 2, so I have 2 ln of modulus root 2 plus u minus 2 divided by root 2 minus u plus 2. And not forgetting the lower and upper limit, 2 and 3. So the next few steps will be quite straightforward. All we need to do is to bring in the 3, substitute in to this expression, minus the case when I substitute in this 2 into this expression. So it turns out that finally we'll have this answer here. Simplifying, we'll get this as our final answer.